So here we have a first order differential equation and the initial value, as well as the solution, the analytical solution for this equation. So we're going to use only 2 lines Matlab to solve this. First of all, we create a variable called, for example, f, like this here, and inside here we're going to write the equation, and after, to get the final results, we are going to call a function called ODE45 for f, and here we're going to put the time span for the solution. Let's say from 0 to 10, and here you're going to put the initial condition, which is 2 in this case. So here we have the code. It's very simple. The third line here plots the results. Let's run it. So here's the solution. Now let's compare it to the actual solution, the analytical solution. So with this code here, we are going to find the plot for the analytical solution of the ODE. In black, we can see the actual solution, and in blue, it's the solution given by the ODE45 function. In case we want a better accuracy for the numerical solution, we can change some parameters like this here. I'm gonna call options and say ODE set relative tolerance equal to 1 to the minus 10, for example. And here I'm going to include these options while calling the function. So let's see how it performs now. So here we have a better solution. The analytical solution is actually covering this numerical solution, so we can see that it's really good now. We can also change the maximum step size, let's say to the -1, and we have almost the same result here. Let's change it for 1, and then we get not a very good solution. So the more we decrease the maximum step size and the relative tolerance, the more time it's going to take to find the solution. Let's see if we choose the maximum step size to be equal to this here. So we can see now that it's taken some time to find the result. Loosely speaking, a stiff differential equation is one whose solution changes very fast. For example, a ball in free fall, when it hits the ground, it changes its velocity very fast. So it goes from a negative value to a positive value. That's, for example, a stiff system. And the ODE45 function is for non-stiff differential equations. But we also have other functions for the stiff differential equations, like these ones here. And among the ODE45 for non-stiff problems, we have the ODE23 and the ODE 113. Each of these solvers have a recommendation for when to use. For example, this one ODE 113, we can use it for problems with strict tolerances. So here we have a very stiff problem. It's actually a second order differential equation, and in the next video I'm going to explain how to use Matlab to solve higher order differential equations. But for now, let's see how ODE 45 performs. It has been trying to solve for at least 5 minutes. I'm going to stop and change it for ODE 15S, which is for stiff problems like this one here. So let's see, actually pretty fast, and we can see that it has a very big change. So that's it.